Welcome to Nuclear Chemistry Video 4. This is Mr. Crump. We are going to discuss half-life today. Please remember to be taking notes as you watch this video. Having watched the video and taken notes, hopefully you'll come into class with some questions about half-life and how we do these calculations. Notice my calculator's with me today. We're going to be doing some calculations, so if you have a calculator and want to work along, you can. But just follow along with the operations we do at the very least. All atoms will eventually break down given enough time. The time required for half of a sample of an isotope to break apart is called its half-life. This is a spontaneous process. All matter that's unstable breaks down at a predictable rate, and we call that half-life. Some isotopes have a half-life of seconds, others have half-lives of billions of years, some longer than the age of the universe. So understanding that, we need to figure out how these calculations work and what it really means. If this is a sample of americium-243, a pure sample with however many atoms you can see there, and we allow it to decay over its half-life, if one half-life passes, which in this case is 7,370 years, half of our americium-233 is decayed into neptunium-239. And as an aside, notice the mass went from 243 to 239. There's only one decay that drops your mass number for AMU, and that would be an alpha decay. So that took 7,370 years. And if another 7,370 years passes, half over again decays into neptunium-239. And can we keep repeating that process until all of that 239, all that americium-243 has become neptunium-239, and that takes about, I think on here is 44,000 years. So that's roughly the idea of how this works. So notice that 1, 2, 3, 4, 5 half-lives went by to where we had virtually nothing left. Moving forward, let's look how these calculations work. Mathematically, how can we determine masses or half-life value or time elapsed given some information? So this is the half-life formula, where A is the final mass or the remaining mass after a decay. A sub O is the original mass of the isotope, and then times 0.5 to the power of N. N is the number of half-lives that have passed, which is the time elapsed divided by the half-life of that isotope. So we can either do this with the calculating formula, which sometimes we'll have to do it with the formula when we're given irregular values, and we can also do it with a table. And both of these are ways you can show your work. Some of these can be done in your head, to be honest, but you need to show work in order to receive credit for a lot of the work we do. If an isotope has a half-life of 330 years, an isotope has a half-life of 330 years. If the initial amount of the isotope was 800 grams, how much remains after 1,320 years? So our time elapsed is going to be 1,320. Our half-life is 330 years. Okay, so we can use those values to calculate N in a moment. We're given an original mass, and we're starting at time 0, where 0 half-lives have passed. So this is after one life, 330 years have passed. We would have but 400 grams remaining. After 2 half-lives, 300 plus an additional 330 would be 660 years have passed. We would have 200 grams. After 3 half-lives, we would have add another 330 years, would be 990 grams, and it would be 990 years. It would be 100 grams remaining of that isotope, and after 4 half-lives, 1,320 years, we would have 50 grams. And that was what the question asked us. What would our final mass be, or what would our final mass be, our remaining mass be after this decay? So let's use the formula. Remaining mass is A, original mass is A sub O, then we multiply that times 0.5 to the power of N, where N is equal to total time elapsed divided by half-life. In this case, total time elapsed was 1,320 years, half-life 330 years. So N is exactly 4 half-lives have passed. Our remaining mass will be equal to our original mass times 0.5 to the 4th. So our calculator, 800 times 0.5 to the 4th power, 50. So our remaining mass is 50 grams. So using both methods, this worked great. The same isotope with a half-life of 330 years has been decaying for 1,650 years, total elapsed time, and 31.25 grams remain. What is the initial amount of the sample? So we're looking for this value here. We've been given our final mass, 31.25 grams. I'm assuming this is our bottom box. When you make a table on your own, you'll be making a free table. You can move things around. We don't know the total time. Oh no, we do know the total time elapsed is 1,650 years. At 0 half-lives, 0 time has elapsed. We don't know our mass. After 1 half-life, time elapsed would be 330 years. After 2 half-lives, 660. 3 half-lives, 990. 4 half-lives, 1,320. 5 half-lives would be 1,650. We add 330 each half-life. Okay, or sorry, each box. So what would our original mass be? Well, we could just simply double our final mass over each half-life to get our original mass, which is what we're going to do. 31.25 times 2. And you can do these in your head, absolutely. Gives 62.5. 62.5 times 2 is 125. 125.2 is 200. Sorry, 125.0 times 2 is 250. 500 and 1,000 grams to begin with. Okay, so our original mass was 1,000 grams. So we're looking for original mass today, or in this question, pardon me. AO times 0.5 to the N. So let's rearrange our formula. I prefer to rearrange before we do our work. Let's do this. Let's divide both sides by 0.5 to the N and just save ourselves the trouble. So our formula will be A over 0.5 to the N is equal to the original mass. So we need N. N is our time elapsed, 1,650 years, divided by our half-life, 330 years. That is 5. Okay. Our A is our final mass, 31.25 grams, divided by 0.5 to the 5th, and that will give us our original mass. So let's do it. 31.25 divided by 0.5 caret 5. 1,000. Our original mass was 1,000 grams. So we did that with the table and with the formula. A sample of radioactive isotope that was initially 1,600 grams decayed for 25,000 years. That's time elapsed. That's our original mass. 50 grams is our final mass. What is the half-life of this isotope? Good question. So let's reveal what we can to say about this. We do know time elapsed was 25,000 years. We know it started off at 0. We know its initial mass was 1,600. And just using simple logic, we know our half-lives. We don't know 1 through 5 here. That's not true. We do know our mass in grams drops by half each time, and this ends up at 50. And so we can quantitatively see that this is 5 half-lives from 1,600 down to 50. What we don't know is the half-life. Well, if it totals 25,000 years over 5 half-lives, then 25,000 divided by 5 gives us 5,000 each. Pretty straightforward how to do that in a table. Okay. Now, if you want to work in a formula, it's a little different. But we can do it still. And we need to be able to do it still, most importantly. So here's our formula. Okay. Keep in mind what N means. N means our time elapsed divided by our half-life that we don't know. So we're going to leave n as n in this equation this time. We're going to have A, which is our remaining mass, 50 grams, and that's going to be equal to our beginning mass, which was 1,600, times 0.5 to the n. What we're going to do is take the log of this entire equation. And so it's going to look like this. Log of 50. I'm sorry. Rephrase. Forgot one little operation there. Let's fix that. Make our work a little simpler to do it this way. So 50 is our original mass. Our remaining mass. Our original mass is 1,600 grams times 0.5 to the n. First things first, let's go ahead and get rid of 1,600. That cancels. And that leaves us with 0.5 divided by 1,600. Okay, back where we were in the equation, we have a little math error we have to fix here. So we have 50 is equal to, that's our remaining mass, is equal to our original mass times 0.5 to the n. All we need to do at this point is simplify by dividing both sides by 1,600. And that gives you 0.03125. And that's equal to 0.5 to the n. When we take a log of both sides, that gives us log of 0.03125 is equal to n times the log of 0.5. Divide both sides by the log of 0.5. And then let's put it in the calculator. That cancels out. We have n all by itself now. We're going to say control 10 to the x gives us log. We're going to tab past the subscript because we're going to work base 10, and it assumes base 10 if we don't put a base 10 there. 0.03125, enter, divided by control 10 to the x, log, tab into the field, 0.5, enter, 5. So n is equal to n is equal to 5. Now if n is equal to 5, and 5 is equal to our remaining mass we do not know, sorry, t is equal to the total elapsed time of 25,000 years, divided by the half-life we do not know. We can solve for half-life quite simply by multiplying both sides by t1/2, then dividing by 5. That gives us t1/2 is equal to 5,000. 5 is equal to 25,000 divided by t1/2, and then 25,000 must be 5,000 divided by to get 5. Let's look at the final example where we're being asked a different question. A radioactive isotope with a half-life of 3 minutes decayed from 100 to 25 grams. This is our original mass. This is our final mass. Half-life, t1/2, is 3 minutes. We don't know how much time elapsed, so let's see. So again, it's A is equal to A sub O times 0.5 to the n, where n is equal to total time elapsed over half-life. We don't have time elapsed, so we're going to have to find n again using logs. So our remaining mass was 25 grams. Our original mass is 100 grams. Times 0.5 to the n we do not know. We can divide both sides by 100 to simplify. That gives us 0.25 is equal to 0.5 n. We take the log of the whole thing to bring that unknown out of the exponent, and it gives us log of 0.25 divided by the log of 0.5 is equal to n times the log of 0.5 over log of 0.5. That cancels, leaves us just with n. So our calculations are control 0.25 log of 0.25 divided by log That's not going to work. I have to do that operation first, guys. Sorry. Enter. Divided by log 0.5. And for number of half-lives is 2. So 2 is going to be equal to total time elapsed over half-life, which is going to be equal to t divided by 3 minutes. Multiply both sides by 3. That cancels. Total time elapsed equals 6 minutes. So let's look at the table version of this. Our original mass is 100 grams, final mass 25. That's times 0 before you began. Time 1 times 2, half-lives pass. One half-life we said was 3 minutes. Another half-life 6 minutes. Okay? The mass in grams would drop in half each time. So the table is often easy, but it only works when our numbers are nice, big, tidy whole numbers. Were our numbers irregular in any way, these logarithmic values would be challenging, and figuring them out in your head on this table would be virtually impossible. So you need to be able to use the half-life formula to solve for any value, remaining mass, original mass, or time elapsed, or half-life. Any one of the 4 is fair game for half-life calculations. But we'll practice in class also. So that leaves half-life calculations. We're done with that lecture. Please come to class with questions about how we did these calculations or how to work with logarithms. It may be new for many of you, but the reality is the calculations aren't bad. We just have to be diligent about our operations. So come to class with questions, and we look forward to seeing you there.